Okay, well, welcome back everybody to session 2 on day 2. I'm really happy to see you all here. We've had some really great talks so far. So it is my pleasure to get started today with Nafaa Chbili, who will be telling us about quasi-alternating links.
Okay, thank you very much. It is a great pleasure for me to be here, and I would like to start by extending my thanks to the organizers for giving me this opportunity to talk about a subject that I have been working on in the past, over the past few years, which is quasi-alternating links. I will start quickly. I guess everybody is familiar with nodes and links. So a link is a one-dimensional compact submanifold of S3, which is without boundary, and the node is a connected such object. The main objective of node theory is to classify these objects up to isotopy, and so it is very important to understand some special classes of links and to classify them or characterize them before hoping for a full classification of all nodes. And the study of links and up to isotopy is equivalent, as we all know, to the study of their projections up to local moves or Reidemeister moves, if you want. So alternating links is a special class which plays a central role in node theory, and I think yesterday's talk of Jessica was about related to this. So a link diagram is alternating if the overpass, if you're starting from any point of the diagram, if you travel along one component of the diagram, you will go over and under, so the overpass and the underpass will alternate. And the link itself is said to be alternating if it has a diagram which is alternating. Otherwise, it is a non-alternating link. So you can see here an alternating node diagram on the left and a non-alternating node diagram on the right. And indeed, the one on the right, it represents a node which is non-alternating. You can never deform this diagram into an alternating diagram, because we know this is a torus node, something torus node, so it is not alternating. So if we look in the node table, indeed, you know, up to 7 crossings, all nodes are alternating. We start encountering non-alternating nodes at 8 crossing. You can see here the 819, 8020, and 8021. These are the first nodes which are not alternating in the table. And then we have many examples after that. So now I would like to define this class of quasi-alternating links. So this class of alternating links, in few words, is just an extension of alternating links. But in which sense? As we will see, the definition is recursive and it looks a little bit unnatural. It comes from the Heegaard Floer homology and the study of the Heegaard Floer homology. So indeed, historically, Ozsv and Szab, they noticed that when they were calculating or computing the Heegaard Floer homology of branched double covers of alternating links, they have seen that this simple homology extend indeed, or this property extend to a larger class of nodes, and they define these quasi-alternating links in such a way that these homological properties are preserved or are extended from alternating to this wider class of links. So I will define, it is defined in a recursive way. We don't have any other definition indeed. So the set of quasi-alternating links is the smallest set which satisfies the following property. So the N node is quasi-alternating. It belongs to Q, to this set. And now if I have a link L with a diagram So I take one of the diagrams of this link. At one crossing, if I smooth this crossing in this, let's say Kaufman, in this Kaufman bracket smoothing, if you want. So L0 and L infinity. Once I smooth, both L0 and L infinity are quasi-alternating. So this is one step in the complexity. So L0 and L infinity are quasi-alternating, and the determinant of L is equal to determinant of L0 plus determinant of L infinity. So if L has a diagram, and in that diagram there is a crossing where this happens, then L is called quasi-alternating itself. So to be quasi-alternating, L0 and L infinity at certain crossing at a certain diagram should be quasi-alternating, and the determinant is summative or additive. This is the minimum required to have this property in homological, in Heegaard Floer homology of the double branched cover of the link. So we can easily prove that alternating knots and non-split alternating links are quasi-alternating. So this is, we can make small induction on the determinant of the link, and we can prove that alternating knots and non-split alternating links are indeed quasi-alternating. The first example of non-alternating quasi-alternating knots are 8020 and the knot 8021 that we have seen in the table. 819 is not, because it is a torus link, a torus knot, so it is not quasi-alternating. But 819, we can find a diagram, and the crossing, as you can see here, the crossing is labeled here by C. If you smooth at this crossing, you will get two knots, one knot and one two-component link, which are already quasi-alternating, which is alternating indeed. And then the property of the determinant is satisfied. So this 820 and 821 are both quasi-alternating. Okay, so I'm not sure about this. So up to 12 crossing, we know which ones are quasi-alternating, up to some conjecture ambiguity. So it is very difficult to use the definition to figure out whether a given knot is quasi-alternating or not. It's very difficult because you have to go through all diagrams and seek for the crossing that satisfy that property. Okay, so especially to say that it is, should look for the diagram. To say that it is not, to rule out the possibility of being quasi-alternating, many or several criteria, several obstructions have been developed. So first, the branched double cover of a quasi-alternating link is an L space. This was the starting point. So the Heegaard Floer homology, L space, it means the Heegaard Floer homology of this space is determined only by the determinant of the link. Okay? So this is a result of Ozsv and Szab. Second obstruction, the branched double cover of any quasi-alternating link bounds a negative definite form manifold with trivial first homology class, first homology group, H1W is equal to 0. This is also Ozsv and Szab. The third point is the more important in our context on today's lecture. The reduced Khofanov homology is thin. So the Khofanov homology is thin, and also, so what does it mean thin? It means, you know, the Khofanov homology is bigraded. KHIJ of L denotes here the Khofanov homology, the reduced Khofanov homology. So it is trivial whenever I minus j is different from sigma L over 2. Sigma is the signature of the link. So this is a result of Manolescu and Ozsv. And same thing happened for the link Floer homology. So it is, these knots are thin in both Khofanov, reduced Khofanov, and link Floer homology with mod 2 coefficients. Okay. So what does it mean here? I have this represents a homology which is Kofman homology, which is thin. So it means it is in two diagonals. It is bigraded, but only these two diagonals in these two diagonals we can meet non-trivial homology groups. So this one is, for this knot to the left, this table is a thin Kofman homology, which is thin. The one in the right is thick, because you see there is one entry, there is one non-trivial homology group outside of these two diagonals. So this was very useful to the study of quasi-alternating links. So more recently, with Khaled Kazakza, we proved that we can say more about the structure of the Kofman homology. So indeed, we proved that the Kofman homology of any quasi-alternating link, it has no gaps of length greater than 1 in the differential grading. So other than it is thin, there is no gaps, no large gaps, let's say. So a gap is a column where there is nothing here, as you can see. So for quasi-alternating, you cannot have a gap of length larger than 1 like that. You cannot have two columns, okay? Neighbor columns side by side where there is no homology. Of course, between the minimum and the maximum. So the Kofman homology, this is the Kofman homology of the triple. It has a gap of length 1, but for quasi-alternating knots in general, it is not possible to find gaps of length larger than 1. So consequently, the Jones polynomial of any quasi-alternating link has no gap of length greater than 1, because the Jones polynomial is the Euler characteristic of the Kofman homology. And then, since there is no gap, in homology, we can prove that there is no gap in the Jones polynomial. Indeed, the Jones polynomial of quasi-alternating links and the signature of the link, they determine the homology. Okay? The Kofman homology is determined by the Jones polynomial, in the case of quasi-alternating links, is determined by the Jones polynomial and the signature of the link. So, for example, we can apply these to prove that many knots are, or certain knots are not quasi-alternating, like Kanine-Bo knots. So Kanine-Bo knots is a family of knots with some interesting property that they share the same, this is Jones polynomial. And we can prove using this property that since they have gaps for certain values, we can prove that they are not quasi-alternating. So what do we know so far about quasi-alternating? If I want to make l'état des lieux, okay, what is known today, at least what I know about these quasi-alternating links. So quasi-alternating links of braid 3 have been characterized based on their normal forms. So Baldwin gave a full classification or full characterization of links of braid index 3, which are quasi-alternating. So they are mainly the closure of this braid sigma 1. So the form is sigma 1 p1, sigma 2 negative q1, etc. This pi and qi are positive integers. So this means that you have an alternating braid indeed. It is an alternating braid plus a twist. So the normal form of a quasi-alternating braid that represent a quasi-alternating knot of a braid index 3 is an alternating braid plus a twist sigma 1, sigma 2 to the power 3n, n is negative 1, 0, or 1. So either there is no twist and then you have an alternating knot, or positive twist or negative twist. You cannot have multiple twists. So this is Baldwin. Quasi-alternating links with determinant less than or equal to 7 have been characterized. So those who have determinant less than or equal to 7 have been characterized by Liedman and Sivek. Third point here, that quasi-alternating pretzel knots have been determined. So you can see Wedemeyer Champanerkar, Kofman, and Green, I think. They classified, we know which pretzel links are quasi-alternating. And this has been extended indeed to multi-sinus links. So all multi-sinus links which are quasi-alternating are known, and this have been done by Kazaksa and my collaborator, Koblan, Champanerkar Ording, and Liska owns. So, and then a complete classification has been obtained by ESA recently. So we know exactly which multi-sinus links are quasi-alternating. If we look at the table, prime quasi-alternating knots with at most 11 crossings have been determined. Okay, so for 11, we know which ones are quasi-alternating. And if you go to knot info, the homepage there, you can find the information about quasi-alternating. It was added recently. I think up to 10 crossings are there. It is there, or 11, I'm not sure. Okay. So I don't have much time, but what I wanted to talk about mainly is how to construct a new example of a quasi-alternating links. We have obstructions that can help tell that this knot is not a quasi-alternating, but how to prove that one is quasi-alternating, it is the difficult part of the problem. So one example, technique have been developed by or introduced by Champanerkar and Kofman, by Abhijit and Ilya Kofman. They proved that if you have a quasi-alternating link, since I don't have much time, so maybe I'll be. So if you have a link diagram which is quasi-alternating at a crossing C, you can form a new quasi-alternating link by doing the following operation. So instead of C, you put a rational tangle, an alternating rational tangle in which extends C. So instead of this crossing, you can put a rational tangle. So you obtain new examples of quasi-alternating links like that. And they gave a proof, a direct proof, where they prove that, use some induction of the determinants and some properties of this operation to prove that starting from an example of quasi-alternating link, I can form more complicated examples by plugging tangles like that. And then we have been able to generalize this to not only a rational tangle like that, but we can put a product of tangles. So instead of one tangle, we can do the same thing, and we can obtain more complicated knots using this technique. And more recently with Kirandip Kaur, we proved that we don't have to limit our study to rational tangles. We can consider more general objects, so we can consider any tangle with some restriction that this tangle extends the crossing. So the tangle should be alternating. So if you have a quasi-alternating link diagram, which is a quasi-alternating at crossing C, like in this example, so then the knot L prime, which is obtained from L by replacing C with an alternating tangle T, whether algebraic or non-algebraic, but it should extend C. We have some technical restriction on how to glue this tangle here. So then what I obtain is a new example of quasi-alternating link or not. So we have few examples here. So for instance, if I start from the knot 8021 and 8020, and I plug in these kind of knots, this kind of tangles, which are non-algebraic, I can form many new examples of quasi-alternating knots and links. So that's all what I have to say today, and thank you very much for your attention. I think I'm on time, so
wonderful, perfect.
It's difficult sometimes.
Wonderful. Let's thank our speaker.
Thank you very much. Thank you.
Wonderful. And do we have any questions for Nafaa? You can either put them in the chat or just go ahead and unmute yourself.
Yeah, sorry, I want to ask a question. It might be a very naive one. First of all, thank you for your presentation. So in the definition of quasi-alternating links, we had two conditions. So this family should have those two conditions, one about the determinant and the other one about, yeah, exactly. So I wanted to ask,
Yes.
if we exclude one of these conditions, we know what a family we would end up with. Exclude condition 1 or exclude condition 2.
I don't know. I haven't thought of it, but yeah, it's interesting. Maybe we can relax this condition and get some more general classes. But yeah, good question. But I haven't. I think the condition on the determinant will not add much. If you keep only the condition on the determinant, I think it will not add much to this class. But the recursive step is more fundamental in this definition. So, good question, sir.
Thank you very much.
You're welcome.
Other questions for our speaker? If not, let's go ahead and thank our speaker again. And
Thank you very much.
about 9 minutes.